with that, why don't we get started? Welcome to Professor Chris Lintott. Thank you for joining us. A research fellow at New College, Oxford. Dr. Chris Lintott holds a professorship in the Department of Physics at the University of Oxford, where his research focuses on galactic evolution and on the application of chemical models to the process of star formation. He is a fellow of the Royal Astronomical Society, primary presenter of the BBC series, The Sky at Night, a lead editor for the American Astronomical Society, a member of the collaboration that is building the Vera C. Rubin Observatory, and, well, a great many other things as well that I couldn't all get written down. But the key thing I should mention for this morning is that Professor Lintott is a co-founder and now primary investigator of the Zoonovas, the world's largest, most popular, and most successful platform for people-powered research. People-powered research in many areas of science, astronomy, and others. And with that, our subject for this morning, I hope that everybody is part of this discussion, and we will take questions at the end. So if you would mute or turn off your microphones, we'll get started with the presentation right now. Professor Lintott, thank you again, and please, the floor is yours.
Thank you very much. Let me share my screen and get that working. Actually, let me do that again, because it's always best when you get it wrong the first time. That's the one. Yep, shared that. Good. And hopefully you can see my title slide now. Please shout if not. Yes, thank you very much for joining me. It's lovely to be at Palomar, even virtually. One programming note, which involves, oh, hang on, I'm on the wrong slide. There we go, which involves this guy. I don't know if you know, but on 5th of November and the closest weekend in this country, we still commemorate the failure of a plot to blow up the Houses of Parliament, which took place on the 5th of November, 1605. So this is Guy Fawkes, the I guess, terrorist in question, being caught in action. So we do this by having bonfires and fireworks, which means that as it's just got dark in Oxford, there are fireworks going off every few minutes, and there's a big display due to start in half an hour. I'm mentioning this because I have a dog that's rather nervous in the house, and he will be providing his own background noises and accompaniment to this talk. He may appear and he may just whine at you. But anyway, that's what's going on. I thought I'd better explain in case you thought somebody was torturing the poor beast downstairs. Yeah, I'm going to talk to you mostly about citizen science, about the involvement of everyone in the research that we do. But as we were just talking about, I have very fond memories of being at Palomar. And this is Cabeus crater, where the Alcos mission impacted. And this is the view from the adaptive optics system on the 200-inch just before that impact happened. And it was an utter privilege to be on the mountain in the dark with a bunch of people with small telescopes outside and the 200-inch pointed at such an exciting target. As somebody who grew up as an amateur astronomer, I've still got my 6-inch reflector in the shed outside. And as somebody who grew up and thinks of themselves as an observer of the sky rather than a theoretical physicist, which my training's in. And it was just wonderful to be there. And I think if there's one thing that connects all of the things that I do, it's that I've never really got over the fact that this subject of ours allows us to look up at a glorious night sky. It's a gratuitous picture at the North American nebula here. But allows us to look up at the night sky and then from that very simple act of observation, draw really fundamental questions about the nature of the universe and the nature of our status in it. And so as an example of that, I've been telling audiences that I think the way we look at images like this one should have changed radically in the last few years. Because thanks to missions like Kepler and TESS, but also an awful lot of work on the ground, we now know that planets are common in the Milky Way, that most stars in this image, most stars that you see if you go outside and look up on a clear night, most stars we now know likely have planets going around them. And to me, that changes our view of the cosmos. This picture that I'm showing becomes a map of possible worlds that we can explore. And I think it illustrates this sort of attitude. I think some of my colleagues who are perhaps more theoretical would say that while the detections are nice and observations are always good, we knew that the physics and chemistry that turn the gas that you can see in the nebula here into stars and the dust, which is blocking out the left-hand portion of the nebula here, into planets. We know that the physics and the chemistry that operated in our solar system obviously is the same throughout the galaxy. So we shouldn't perhaps be surprised by this result. But the observer in me says that knowing that the planets are there is a very different thing. And I think you really see that if you look at images like this one. This is an image of the star HR 8799 from the European Southern Observatory's Very Large Telescope. And actually, that's precisely what it isn't. This is an image not of the star HR 8799, because an instrument called a coronagraph has been used to block out the light from the star. The yellow thing is obviously a marker. That's not what stars really look like. I had to ask that after one of these talks. But the exciting thing here are the four blobs that you can see around the star, because if we animate this over the course of several years, this is 10-year-old data now, we can see that those blobs are in fact planets. And this is an image of planets moving in their own solar system. And you've seen cleaner, more beautiful, animated versions of this a million times, I'm willing to bet. Whenever anyone talks about our solar system on TV, or in a talk like this, you show an animation. But this is real. And being able to watch planets going around their star makes me extremely happy. Now, of course, you can't, and this system is interesting. It's sort of a blown up version of the outer solar system. Each of these is 2 to 3 times the size of somewhere between Jupiter and Neptune, and they're on 45 to 460-year orbit. So it's not quite like our solar system, but it's a relatively nearby system that's of interest. Now, you probably know that I can't show you most of the planets that we know about. Most of them are not able to be seen, even with coronagraphs like this. And the issue, which I think is slightly surprising, isn't that the planets are too faint. Were they to be on their own, they'd be well within the reach of our surveys, but it's that they're too close to their stars. The glare of the star makes it very difficult to pick out the planet, like trying to detect a firefly flying in front of a stadium floodlight. And so we use these indirect methods. And the one that's had the biggest impact, though not by all means the only one, is of course the transit method. And this is observations from the park outside our office in Oxford from a few years ago, where Venus crossed in front of the sun. These transits are rare. Venus is only observed at most twice a century to do this. The next one's 100 years away, or so, actually a bit less than that now, I think. But on the right is the physicist's view, where this is just a graph made with a light multimeter that's just recording the brightness of the sun. And you can see that when Venus is in front of the disk, the sun is about 0.1% less bright. And when I'm showing this, particularly to students, I often make the point that this sort of astronomy isn't what people think of when they think about how modern astrophysics is done. We have a reputation, I think, for being really rather clever. People think of, astronomers as people who sit perhaps under a waterfall contemplating the deep mysteries of the cosmos and come out with a fully formed theory. But actually, what we really do is make simple observations really, really well. So if you can monitor the brightness of a lot of stars very, very, very carefully, then you can catch these tiny dips that occur when planets get in front of the star. And if you monitor enough stars, then you get lucky often enough to make this a worthwhile pursuit. But you have to do it accurately. And when you do, you can deduce the presence of lots of different planetary systems. So I've been telling people that everyone should now have their own favorite planetary system. Solar system taken, but you can pick one of the others. So this is mine. This is the K2138 system, discovered by Kepler in the later stages of its mission as a 5-planet system. And this is to scale. So the orbits are to scale and the planets are to scale, but they're not to scale relative to each other. And so you can see this is a 5-planet system. We've got B, C, D, E, and F. Luckily, they're in that order, so that helps. And the first thing you should notice is that this system is cramped. All 5 of these planets are crammed within about 10 million miles of their star, so closer to the star than Mercury is to the sun. So the best analogy for this, or best analog for this system in our solar system, is probably something like the Galilean moons of Jupiter, rather than our main planets. But nonetheless, these are planet-sized bodies, and there's a pattern to their orbits. They're arranged in what's called a resonant chain. So for every 3 orbits B completes, C completes 2. For every 3 orbits C completes, D completes 2. For every 3 times D goes around its star, E goes around twice. And for every 3 times E goes round, F goes round twice. So there's this 3 to 2, 3 to 2, 3 to 2, 3 to 2 pattern. And this is the longest such chain of that 3 to 2, 3 to 2 pattern. And so that has a couple of consequences. One is that we can have some fun. So this is an animation by my friend on Twitter, Matt Russo. And so what he's done is he's created an instrument out of the solar system. So each time a planet completes an orbit, it sounds a note. And the pitch depends on the size of the orbit. And the point here is really that seems musical. And the reason that seems musical, hopefully you can hear that, by the way. The reason that seems musical is that there's this 3 to 2, 3 to 2 pattern, which means we get a nice chord out of this system. So it's a harmonic system. And the other thing that the fact this is in resonance does is it tells us that these things are must have formed together. So we think the planets that are this close to their star formed further out in their solar system and moved inwards. The fact that these are resonant patterns suggests that process was slow rather than fast, and probably ordered rather than chaotic. Maybe that these planets moved in together. We can also use planets like this to work out. We can look at timing, changes in timing between the interactions of the planets, which might tell us about their composition and mass. So this is a planet system we can find a lot out about. But none of that is why it's my favorite. It's my favorite because it was discovered not by professional astronomers, but by a bunch of volunteers on a website called Planet Hunters, which my team had built. And one of the discoverers was this guy. This is Andrew Gray, who is an amateur astronomer in Darwin in Northern Australia. And this shot is from the TV interview he gave after we got to email him and tell him that he'd discovered 5 planets. I really enjoyed watching Andrew and others get credit for this discovery. It's very pleasing. And Andrew in particular, I thought was great. You know, one doesn't want to pander to national stereotypes, really. But, you know, Andrew's a proper Australian. And when he was asked how he wanted to celebrate his discovery, he said he was going to take his Dobsonian telescope out into the desert and have a beer with it, which I think is probably the most Australian response to a discovery that I can imagine. Now, Planet Hunters has been running for many years. We ran throughout the Kepler mission, but we're now using data from TESS, which is NASA's latest planet hunter, which looks for about 30 to 90 days at a time at the brightest stars in the sky to see if they have planets. And my student, Nora Eisner, who's pictured up here in the top right, has been working hard to make sure that we can still find planets in the test data. And what's really interesting is that not only is Nora succeeding, we are, with the help of hundreds of thousands of volunteers online, finding planets. We're finding different planets from other people. So this graph shows a couple of years, it's probably 6 months out of date now, but this is every planet that was found in the first 2 years of test data. Actually, I should probably be accurate. This is every planet candidate found. So these are things that are likely to be planets, but we haven't insisted that we've gone and done confirmation yet. The y-axis on the left is the radius. So the higher up you are, the larger you are as a planet, with the Jupiter-sized things at the top, Earth-sized things at the bottom. And then that's the orbital period on the x-axis. So as you move to the right, you go from planets that whiz around their star in a matter of days to those that take weeks or months. And in blue are everyone else's planets, and in orange and red are the planets that Nora and the volunteers of Planet Hunters are finding. And so there's this really clear division between the two. And so what's happening is that we're finding the long period planets in the test data. And this is because we have people looking at the data itself. Most of the other efforts use automated methods that look for repeated transits, because you look for the planet going past once and then again and again and again, and you can use that repetition to build up your confidence that there's something there. Most of those methods fail if the planet's only been seen once or twice in the observing period. Whereas if we have a suitably trained volunteer, somebody who's seen a few light curves and can take a careful look, you spot the individual transits, and then we're able to follow them up or check them out in other ways. So this isn't a surprising result, but it's very gratifying that we're able to help people make these discoveries. It's gratifying partly because I think when I was growing up, the idea that I'd be involved in a project that found planets would have been beyond my wildest dreams. And sending people emails that say, hey, you remember that website you visited where you actually found a planet is just wonderful. But you know, I've always wanted to make discoveries myself. I think it comes from being an observer. You want to be the first to see something. And I have found, I'm pleased to tell you, absolutely nothing in my career that would count as a discovery. I came close once with the 6-inch reflector that I was telling you about. My favorite object in the night sky is the Orion Nebula. I think many of you will know that. I think even in a small telescope, if you spend enough time, the nebula never ceases to be boring. You see some of the three-dimensional structure, that green color, the way the gas wraps around the hot young stars that have formed in the trapezium at the center. It's a beautiful object. And I remember one particular night when I was 14, observing the Orion Nebula, nudging the telescope and seeing this cluster, which is just to the north of the nebula, swing into view. And I'd never heard of a star cluster near the nebula itself. In the nebula, sure, but not nearby. And so but there was something striking about this cluster. And I remember this was before, if you can believe such a thing, before we had the internet at home. And so I had to go and get a book. You'll remember books. They're these things that are behind me. They're a bit like the web, but they're slow. Anyway, I got Sky Atlas 2000 out, and for some reason, the cluster's not in the atlas. And so I remember getting a pencil and marking it out as Lintott 1. It turns out it's NGC 1981. It's been known for hundreds of years. It's not a discovery. I don't know why it's not on the Star Atlas. They corrected it in later editions. But I had this moment where I thought I'd made a discovery. But I came to think over subsequent years that was the end of my naive childhood, dreaming that I could make a discovery by being the first to see something. I learned as I went through my academic career that these days, astronomy is not often done by 14-year-olds with small telescopes. So I'll remember to mention, I hope, the contributions of amateur astronomers shortly. But it's done by building experiments like this. This is the Sloan Digital Sky Survey, which is what you get when you get particle physicists to build you a telescope. This is an experiment, not an observatory. It was designed to operate in a particular way. It was designed to have an 8-year campaign during which it basically just let the sky pass overhead, and it used its camera to take images in 5 filters of the whole sky, identifying hundreds of millions of objects. And on the clearest nights, Sloan went back to the million or so objects in that sample, which had been identified because they were fuzzy blobs, essentially, as potential galaxies. And then it used a spectrograph to measure the distance to them. So it was building up a 3-dimensional image of the cosmos. Here's an example from a rival project from 2DF that was doing much the same thing. And what you see here is that each dot is a galaxy. We're at the center. And Sloan and 2DF and surveys like this gave this remarkable result that the universe is lumpy on a large scale. And cosmologists are interested in this because the degree of lumpiness gives you a constraint on how much matter there is in the universe. It's some of the strongest evidence for the fact that we have a universe dominated by dark matter comes from this sort of work. But also we can constrain the expansion rate by comparing this to observations of the early universe and so on and so forth. But a nice byproduct of this work was that we got lots of lovely pictures of galaxies. So even though Sloan did the experiment that it was designed to do, it had this bycatch, if you like, of beautiful images of galaxies. And it's not very clear why that's so. There was a meeting apparently in a windowless room in Chicago's O'Hare Airport, where Jim Gunn, the presiding genius of some of the design of Sloan, insisted that the cameras be good enough and the exposures be long enough to reveal the galaxies out to some distance as not just points of light, which would be sufficient for the cosmology, but also good enough to say something about the shape and the color of the galaxy. And the shape is really important. These are 2 galaxies. These are both Sloan images, though I cheated and picked relatively nearby galaxies. Most galaxies in Sloan look like blobs. I picked these 2 galaxies because they're about the same brightness, and therefore we assume the same mass, more or less. But they're obviously very different from each other. And they're different in color. And as you probably know, because the blue of the spiral galaxy, or the blue of the left-hand galaxy here, is mostly because of light from massive short-lived stars that will only exist for 10 or maybe 100 million years. The color of a galaxy tells you about what's happening now. It tells you about where and when recent star formation has happened. And then, so one of these galaxies has had recent star formation, the other one hasn't. But the shape of a galaxy, which is a contrasting measurement, tells you about the entire history of the galaxy. It tells you about how it's interacted with its surroundings. It tells you about the history of star formation in the galaxy. It tells us whether it's led a relatively quiet life or whether it's one where it spent a lot of time interacting with neighbors and merging with other galaxies. And so if I have images of 1 million galaxies and I can label them by shape, then I can learn a lot about the galaxy population. I can learn, for example, whether different types of galaxies live in different parts of the universe, something that might tell us which processes are important in shaping galaxies like the Milky Way. Trouble is, color I can do automatically. I can measure how bright one of these galaxies is when viewed through a blue filter and how bright they are when viewed through a red filter, and subtract one from the other, and I've got a numerical measure of color. Shape is more difficult. At the time, we thought this was a simple enough problem. We have students. A PhD student called Kevin Shawinski in Oxford in 2006 set out to tackle this problem. And Kevin looked at 50,000 galaxies, spending 2 weeks doing nothing but going spiral, spiral, elliptical, 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 spiral, spiral, and so on. And I always tell people the first result of Kevin's thesis was that a student will look at 50,000 galaxies before they tell you where to stick the rest of them. I'm translating slightly. And unfortunately, the second result was that Kevin was better than a computer at doing this at the time. So it really mattered to have a person look at these galaxies. And so I was trying to work out what to do with the other 950,000 galaxies if Kevin wasn't prepared to look at them. I tried taking him to the Royal Oak pub here in Oxford and buying him beer, but he was adamant he wasn't going to. And so I thought, I grew up as an amateur astronomer. I know about astronomical societies. Maybe we could ask for help. And inspired by a few projects that have been run, particularly by NASA in advance, we created a little website called Galaxy Zoo. And Galaxy Zoo was designed to ask the simplest useful question. We showed people a random image from the Sloan survey. And then we said, okay, is it an elliptical or a spiral? Is it a merger? And there's a button for the occasional star that slipped through. And the idea was that I would talk to amateur astronomy groups, maybe 50 people would come and watch, maybe 50 people would go home and classify 50 galaxies each. And in a year or so, we thought we would have sorted through the million galaxies. But it turns out it's really hard to succeed slowly on the internet. And very quickly, in fact, the day after launch, we were receiving 70,000 classifications an hour. So that's more than Kevin managed in 2 weeks. So it's the Kevin fortnight is the unit of galaxy classification. And because we had so many, we could have many, many people look at each galaxy. And that allowed us to find some quite subtle effects. And you'll notice from the screen that as well as asking whether it was an elliptical or a spiral, we asked which way the spiral arms were rotating, whether it's a clockwise spiral, sort of an S shape, sorry, a Z shape, sorry, a Z shape, or an anti-clockwise galaxy, an S shape. And the direction of the arms tells you which way the arm is spinning. And we did this because there was a paper that we just didn't believe from a cosmologist particle physicist called Michael Longo, who's a lovely bloke, but he'd looked at 2,000 of these galaxies and then concluded that the universe had more anti-clockwise galaxies than clockwise. And this is a result that makes no sense whatsoever. This is, for starters, Sloan covers a quarter of the sky. So you need a cosmic conspiracy that means different parts of the cosmos, which haven't really been in contact since just after the Big Bang, can coordinate and agree that they're all going to have a slightly higher odds of having anti-clockwise galaxies. And second, this result breaks the most fundamental rule of cosmology, which is the Copernican principle, which is the idea that any large-scale observation of the universe shouldn't depend on your position on it. But if we're seeing more anti-clockwise than clockwise galaxies, then you could fly to the other side of them, in theory, look back and see more clockwise ones. And so we didn't believe this result. And so we asked this question thinking that it would be a good test to make sure our results were frankly sane. And I remember working with my colleague, Kate Land, whose idea this bit of the project was. And I remember being in the office when she ran the code to analyze our new classifications of hundreds of thousands of galaxies and discovered that there were indeed slightly more anti-clockwise than clockwise galaxies in our data set, a result that I think neither of us expected. Now, we could have declared that cosmology was broken, that our model of the universe needed serious adaptation, and we were tempted. We certainly could go down the corridor and talk to friends and see what they made of it. But extraordinary results require extraordinary proof. And without telling anyone else, Kate and I decided we should do another test. And so what we did was, without telling anyone, we reversed all the images in the site so that we were now showing the mirror images of the galaxies. And if this had been a real result, we should have seen more clockwise than anti-clockwise galaxies. But we didn't. We still saw more anti-clockwise galaxies. Sorry, counterclockwise for Americans. So apologies, I forget that that's different. So we still saw more counterclockwise galaxies. And so it's actually not the universe that's odd, it's us. There's something about how we perceive these fuzzy images that makes it easier to see a spiral if it's counterclockwise rather than anti-clockwise. And it's a tiny effect. We had enough people and enough sensitivity that we could do it. Now, I can't go on to tell you all about the science that we've done with Galaxy Zoo. Over the 15 years since the project launched, we've done an enormous amount, and we've actually gone and used different data sets. So we've now used Hubble Space Telescope surveys to look not just at the local universe, which Sloan's million galaxies let us do, but we've looked at the distant universe as well. So for example, from left to right, this is moving back in cosmic time, maybe as many as 6 or 7 billion years. And the line here, or the points here, just show the fraction of disk galaxies that have bars And so you can see, slightly to my surprise, that barred galaxies are a recent phenomenon. So this fundamental division that exists in the Hubble tuning fork, our normal classification of galaxies, where we split spirals into barred and unbarred spirals, is really only something we've had to worry about for the last couple of billion years. So something in the universe has changed to make barred galaxies more plausible. We've also done things with subsamples of the data, and I want to spend a little bit of time on one result here. So let's just remind ourselves that here's the Milky Way. This is our best map. It's a disk galaxy with a bar, at least a bar that's been there recently. We're halfway to the edge, but at the center, there's a well-known source, which we think is a black hole. And we think it's a black hole because we've watched stars in this data from Keck, from Andrea Ghez's group. We've watched stars orbit something that otherwise doesn't shine, the source at the center of the galaxy. And because we know the mass of the stars and because we understand orbits, we can work out the mass of the central source, particularly because of this one star SO2 that we've watched do a complete orbit. And it turns out that the black hole at the center of our galaxy weighs 3 to 4 million solar masses. We know that other galaxies have black holes too. You've probably seen this image, which is from the Event Horizon Telescope. So this is using radio telescopes all over the world to look at the center of a galaxy called M87, nearest big gap, the biggest galaxy in the nearest big cluster, and reveal the shadow of its black hole. But I wonder if you've stopped to think, why have we got an image of the galaxy, a distant galaxy's black hole, and not our Milky Way's black hole? And there are a couple of reasons for that. One is, it turns out there's a problem with the variability of the light we get from the Milky Way. It's changing more rapidly. It's a technical problem. But also it's just that the black hole in M87 is much more massive. That's why it powers things like this jet of material that's expelled from the region around the black hole. It's because M87's black hole is about 10 times larger than our own Milky Way. And actually, it turns out we should have been able to predict that. There's a rule of thumb maybe in galaxies, which is that the more massive the galaxy, the more massive the black hole. Those two things go together. So M87 is further away, but it's a more massive galaxy. It has a more massive black hole, so the scale of the features around it are larger, and it's an easier target for the Event Horizon Telescope despite the distance. But why should that rule exist? It's actually, it may sound like common sense that those two things go together, but actually, to a physicist, it's pretty confusing. The Milky Way's black hole is 3 or 4 million solar masses. We call it a supermassive black hole, but that's peanuts when compared to the mass of the galaxy itself. The Milky Way has 100 billion stars in it, so it's at least 1,000 times more massive than the black hole in its center. So how does this component at the center, which is only less than 1% of the stellar mass, much less than that of the whole thing, how does that influence the rest of the galaxy, or how does the rest of the galaxy influence the black hole so that they grow in step like this? It's a big mystery. Now, one possibility that's been proposed blames the whole thing on mergers. So we know that galaxies merge. This is a simulation of the next few billion years of our galaxy's future. You probably know that in our local group, consisting of Triangular and Andromeda, we're heading for a collision with the Andromeda galaxy. We'll actually form one single system, which I'm afraid to say my colleagues have decided should be called Milkdromeda, which I think is an utterly unpoetic name, but I'm struggling to think of anything better. Anyway, the two galaxies merge. This triggers a lot of star formation, a nice cosmic dance. It should be spectacular. The sky will light up with stars as both galaxies use up their gas. But eventually the galaxies come together to form a single galaxy. See, the shape is changing. And eventually the black holes at the center of these two galaxies will merge. An event that may be detectable, or events like this might be detectable with future gravitational wave experiments. So if galaxies mostly grow by merging and their black holes collide each time, then we've explained my rule, because the two will grow in lockstep. As galaxies merge and become more massive, so their black holes will merge and they'll become more massive too. But this is an idea that needs testing. We realized that with the Galaxy Zoo data, we could test this. So this is a normal spiral galaxy seen edge on. You've got the disk. And then there's this bulge of old stars, relatively subtle in this galaxy that exists at the center. Well, it turns out there are rare spiral galaxies that have no bulge or nearly no bulge at all. And along with my colleagues Brooke Simmons and Becky Smethurst, who, by the way, is Dr. Becky on YouTube, and you should definitely watch her videos, we found a set of 113 galaxies in the Galaxy Zoo data that have no bulge, but which have growing black holes. So the point sources at the center of these galaxies are not stars, they're not bulges. That's light from material that's surrounding growing black holes. These are AGN. And so we said, okay, so if black holes mostly grow through merging galaxies, these bulgeless galaxies have never had a merger, because any merger would kick stars out of the disk and build up a bulge. So these are guaranteed merger-free galaxies. And so we said, okay, we can look at their black hole masses and we can look at their mass and see if the rule holds. And to our surprise, we found that it did, that these galaxies had the black hole masses that you'd expect for galaxies of their size. And so we found out how not to explain this relationship between the black hole mass and the galaxy mass. And it's still a mystery that we're working on today. Now, I've gone into quite some detail because I wanted to convince you that these classifications are not just a fun project to do on a cloudy day. They're actually producing real science as well. And it turns out that we can do this with things other than galaxies. For example, penguins. One of the things that happened when we launched Galaxy Zoo, I always like to imagine at this point that somebody's just woken up and tuned into this talk at this point and is wondering why there's a penguin on the screen. But one of the things that happened when Galaxy Zoo was a success was that other scientists who also had this problem of having acquired too much data and needing help to go through it, and started calling us up and saying, you know, could your people who do galaxies also help me? And one of the first calls we got was from a zoologist in Oxford called Tom Hart. And Tom, for years, has gone to the same parts of the Antarctic Peninsula, the bit that sticks up towards South America. And he's gone and counted the penguin colonies. And this used to involve him literally going to the same place every year, asking the penguins to stand still, and then going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. This is an inefficient process. And it's also subject to quite noisy data. Maybe one year it'd be raining and the other year it wouldn't. Maybe one year the penguins would have nested a month earlier. It'd be at a different stage of their annual cycle. Maybe sometimes he'd be there in the afternoon and the tourist boat had turned up earlier on and disrupted things. And because what he was interested in was understanding how the penguin colonies are reacting to climate change, to tourism, to even the effects of Tom and co visiting, and he needed better data. Luckily, cameras have become cheap in the same way that some of the large surveys in astronomy have been driven by advances in technology. Ecologists have discovered that you can buy cheap off-the-shelf cameras that run off a car battery, which can be abandoned on sticks in Antarctica for a long period of time. So now Tom goes to the Antarctic once a year, hitchhikes on cruise ships to go from place to place, and all he does each time is grab the card out of the camera, replace the battery, and he comes back to Oxford with 8 million images of penguins each year, which we put online using the same software that powers Galaxy Zoo. And we created Penguin Watch. So you can go to penguinwatch.org and you can help us count penguins. Hundreds of thousands of people have. Hopefully you won't be too disturbed when I tell you that every time I look at this video, I remembered that our original name for this project was Penguin Hunters, which I think you can see in the design, but apparently that's not the right tone. Anyway, Galaxy Zoo and Penguin Watch are all now part of the Zoonovas, which is a collection of about 200 projects. The astronomical ones include spotting asteroids in Hubble data, keeping an eye on solar storms, and classifying infrared images of our galaxy. I've already talked about planet hunters. I'll mention finding supernovae in a moment and so on, but also transcribing ancient papyri, rescuing old weather records, looking at scientific magazines from the 19th century, and keeping an eye on raccoon populations, and pretty much anything you could think of is involved in Zoonovas. And more than 2 million people have signed up and contributed to these projects. And so this is what we mean by citizen science, this sort of collaboration between large crowds of people and a few professional scientists. And it turns out that this idea of collaboration with others shouldn't have been new to us, and it's actually got a long history. I think the oldest successful piece of scientific crowdsourcing or citizen science I can find comes from Edmund Halley, a predecessor here in Oxford. This is his map of the track of an eclipse, a total eclipse of the sun that crossed central England in the year 1715. And this image is taken from a pamphlet that Halley and a collaborator produced, which you could buy at the time for a penny, which had the predictions. And then this text at the bottom explains a little bit about what an eclipse is, but it also asks people to time the beginning and the midpoint of the eclipse and to send those observations to Halley. He's interested at the time in refining his measures of distance in the solar system, so working out the distances to the moon and the sun and thus to the other planets. So this is a crowdsourced experiment. Halley also got professional astronomers involved. A group observed from outside the Royal Society in London, though that's not the best observing site then or now. He wrote to people in Oxford, where it was cloudy, as per usual. And he wrote to people in Cambridge, where the observatory was in the charge of the Reverend Mr. Roger Coates, who I think deserves infamy because it was beautifully clear in Cambridge on the requisite day in 1715 in April. And he had to write to Halley and say that he'd meant to observe the eclipse, but he'd been oppressed with company, which I think means that his friends turned up and distracted him, which is not really a very good excuse. But 200 other people sent their observations to Halley, and they were published and used to refine his models. So these are amateur astronomers, citizen scientists contributing to research, something which I'm sure lots of you on the call know happens today, whether it's through organizations like the AAVSO, who have more than 100 years worth of data of people looking at variable stars, to people discovering comets. This is Borisov, the first big interstellar comet discovered by a Russian amateur, or even not necessarily looking through telescopes and imaging, but projects like those coordinated on the website unmanned spaceflight.com, where people are reprocessing data from historic and present day missions. So this is an image of a moon of Neptune, which was rescued from the Voyager archives by a guy called Ted Strike. And this is a moon that had otherwise not been captured in the image, but there it is. No one knew that it was transiting, but he worked it out and found it. So hopefully I've convinced you that it's useful to look through large amounts of data, and that it's fun to do so, and that we have these benefits of making lots of discoveries. I want to take the last few minutes to convince you that that's still going to be useful in the future, because I'm sure it's occurred to some of you that these days, the idea of looking at images is rather quaint because the robots are coming. We know that this sort of pattern recognition in image data is something that modern machine learning routines are really, really good at, particularly methods that fall under the banner of deep learning, things you read about in the press when Google have built a computer game playing robot, or where it's predicted that 30% of us will lose our jobs to robots shortly. Actually, the kind of technology that's behind the attempts to build autonomous cars. Well, that's just pattern recognition. And you may be thinking, well, we're just these days, fine, in 2006, 2007, we needed people to look at these images. But what about now? Well, it turns out that there's a property of deep learning that's kind of fascinating. And I'm going to illustrate this using images from another Zoonovas project. So this is a project called Snapshot Serengeti, where people classify images from motion-sensitive cameras in the Serengeti National Park. And these are all obvious examples, but let's say we care about giraffes. Once we'd assembled hundreds of thousands of images of giraffes because people went on the site and labeled them. We were able to train a machine. You do that by showing it lots of pictures saying, this is a giraffe, this isn't a giraffe, this is a giraffe, this is a giraffe, this isn't a giraffe. And so we've done this. You can build a pretty good giraffe detector using the data. It's open source. You can use it if you have a need to detect giraffes yourself. If you care about some of the other animals, like this thing, this is a zorilla. It's a small skunk-like object that turns up in 1 in every 3.6 million photos taken by the camera network. So we have about 10 images of this thing from our cameras. I can't train modern machine learning on a zorilla. For that, you need people. And in space, we have lots of zorillas, and we really care about them. In astronomy, we care, particularly observers like me, care about the unusual objects. And so what we need to do is find a way for humans and computers to work together to collaborate to find the unusual things. And we've started doing that already. So if you go to the modern version of Galaxy Zoo, we're now sorting our way through the southern sky. You'll see there's a little button that says Enhanced. And if you go to Enhanced, you'll see a set of data that's been filtered by computers. So the computer has taken the things that it's confident about and classified them, and everything else ends up being shown to the volunteers. And by working together like this, two things happen. Firstly, we're able to get through the data much faster. So there's much less work to do. The computer turns out to be about as good as 10 random volunteers, but not as good as the whole crowd. The second thing that happens is that it turns out that because we train the computer based on the input of Galaxy Zoo volunteers, it sees these galaxies in a way that makes sense to us, something that's not guaranteed from this sort of deep learning. Sometimes computers make very strange decisions, but actually the representation of the galaxies in the mind of the computer here is useful. And so we can do things like build extra tools where you give it one galaxy, in this case, an unusual ring on the right, and it will return all of the similar galaxies to that one. And so this is a very useful synergy between human and machine. There's one last trick we humans have in our sleeves though, and that is that we're good at getting distracted by unusual things. So in Galaxy Zoo, the canonical example is this thing. This is an object known as Honey's Voorwerp, named after a Dutch school teacher, Hanny van Arkel, who found it in the original Galaxy Zoo data. This is actually a Hubble picture of it from some of the follow-up work that we did. And you can see why this might require human insight. If I give this image to a galaxy classifying computer, it might tell me that there's a spiral, perhaps a dusty spiral at the top of the image, but not that we should be scared of an evil version of Kermit the Frog or a slightly poorly rendered image of a Klingon battleship or whatever it is that's going on at the bottom. But as a person, Honey did the really natural scientific thing of saying, what's the blob? Voorwerp, which is the name she gave it, turns out to be Dutch for thing, by the way. So we use the name thinking it was technical, but it turns out to be thing. And the Voorwerp's a fascinating story. We managed to get a spectrum of it, which told us it was at the same distance as this galaxy. So it's big. And the spectrum also told us that the gas was hot. It's about 50,000 Kelvin. And that there aren't any stars in the Volvo, or at least not any hot ones. So the mystery became, how has this gas been heated to such a temperature? And the culprit, we thought, was the black hole at the center of the nearby galaxy. You can see in this image that the galaxy looks disrupted, maybe from a merger. That might have funneled material down onto the black hole at the center. Sometimes you get a jet of material that comes away from the center of such a system. The Voorwerp is directly in line to be hit with the jet. So all of this made sense. All we needed to do was check that there was hot gas at the center of the galaxy, which you do with a orbiting X-ray telescope. We used XMM Newton, and we saw absolutely nothing, no hot gas at the center of this galaxy. And so this was puzzling. But what we think happened is that we caught this galaxy in a moment of transition. The light travel time from the center of the galaxy to the Voorwerp is 50,000 years. And so the Voorwerp tells us what was happening 50,000 years earlier than we get from our current view of the center of this galaxy. And so we think the Volvo is telling us that 50,000 years ago, this would have been the brightest quasar in the sky. It would have been bright enough to see with binoculars, magnitude 8, we think. And what's happened is that the black hole at the center has gone very quickly from being active to being quiet. So the Volvo was a clue that galaxies don't really come as either active galaxies or quiescent ones, as people might have thought, but they can switch rapidly between the two. And we've since found other Volverpen, which look like this, and which have allowed us to show that this sort of behavior is really, really common. So, yes, we can get machines to do a lot of the work for us, but we need to show the unusual and the rare stuff to volunteers so that we can identify the things that are worthy of our attention. And that's going to be more true as we build bigger telescopes and bigger surveys. This image from March shows the installation of the main focus cage for the Vera C. Rubin Observatory's LSST survey telescope. It's the Simone telescope. This project has a lot of names. This is a telescope that's as big as some of the biggest telescopes in the world today. It's an 8-meter mirror, but it's designed with a squat optical design to give a wide field of view. So it's going to act as a survey telescope. And it will, in fact, scan the whole sky every 3 nights or so, producing 30 terabytes of image data a night and about 10 million alerts a night telling us that things have changed. And in all of that data, there will be wonders that we know to expect, thousands of supernovae, hundreds of thousands of asteroids, beautiful deep images of merging galaxies and galaxies that used to merge, all sorts of things. But there will also be things in that data set. I will bet you almost anything that there are things in that data set that we don't know to expect yet. When you have such a large amount of data, we're going to need volunteers to look at a proportion of it to help us find the unusual things that are worth following up. And we're still going to be in a position where our greatest survey of the sky, its output will depend on persuading hundreds of thousands of volunteers to come and share this adventure of exploring data with us. And in that sense, we're not that different from any other set of volunteers. I want to finish with this guy. This is Arglander, who is a great Prussian astronomer in the 19th century who pioneered the systematic study of variable stars, stars that change their brightness. And he did that partly because he appealed to anyone who was an observer to send him their data so that he could use it. And so in writing his appeal, he said, could we be aided in this matter by the cooperation of a goodly number of amateurs? We would perhaps in a few years be able to discover laws in the apparent irregularities of stars. So he's trying to work out why they change in period. And then in a short time, we would accomplish more than in all the 60 years have passed since their discovery. I have one request, which is this: that observations must be made known each year, because observations buried in a desk are no observations at all. Should your observations be entrusted to me for reduction or even publication, I will undertake the task with joy and thanks, and I'll answer all questions with care and with the greatest of pleasure. I think that's pretty inspiring, and I'm happy to answer your questions with care and with the greatest of pleasure. Thank you very much.
Professor Lintott, thank you very much. And the floor is open for questions.
Let me start with kind of a left-handed question.
Good.
The notion of a cognitive bias with observers looking at the spiral galaxies maybe suggests that you can understand more about human cognition and kind of reverse engineer that element of the process. Is that even a consideration?
Yeah, so, well, being astronomers, the first thing we try to do is measure how people behaved and subtract it from the data. So we were able to measure the size of the effect and then show that once you took that into account, that there was no bias, that there were the same number of anti-clockwise and clockwise galaxies. Though I should say Michael Longo doesn't agree. He's done his own experiments since. We also found some fun things like it turns out two spirals that are near each other tend to turn in the same direction, which tells you something about how they got their spins. But yes, we really should. And then there are a couple of theories as to why this bias might exist. And what I really want to do is look at the data for people who are using the Hebrew version of the site versus those who are using the English one, because Hebrew reads right to left, not left to right. And it's been suggested that it's to do with the way your eye encounters the shape. So I'd like to rule that out. And then there are various things to do with perceiving the galaxies as 3D objects that people have suggested. So yes, we could end up experimenting, but sadly, I keep getting distracted by studying the galaxies rather than this important research. It's a really good question.
Michael and Kathy, you had a question. Would you like to ask it, or I'll read it off the chat?
I can take it off the chat if that's easiest. Is that all right?
Okay.
Yeah. So the question is, correctly, they say that you can only use the transit techniques to find planets with planetary systems that are edge on, because you need the planets to be going in front of the star. So how do you find the ones that are not edge on? So yeah, you're absolutely right. And the fact that the transit technique is so successful tells us that planets are common. Because the fact we found lots of transiting planets when the odds are 1 in 100 or something that an Earth-like planet would transit tells you that there are 99 that you haven't found this way. So partly we guess that they're there because we know that, but there are other techniques. So as you say, barycenters, yeah. So one way of doing this is to look at the spectrum of the star, and then you see how it wobbles as the planet goes round. So that's the radial velocity method, and that works too. And ideally, we get both transits and radial velocities for the same system, and they cross-check. And that's been done a lot. There are also some less well-known techniques. There's microlensing, where you look at the influence of the planet's gravity on the star, and a few others as well. What these techniques all have in common, though, is that they're most sensitive to massive planets close to their stars. So there's a lot of work done to try and understand those biases. And that's why Planet Hunters is really important, because we're coming in at an orthogonal angle to everyone else, finding different planets and helping people understand what the biases are in their methods. Thank you for the question.
I'm very surprised that the search wasn't computerized a long time ago. It seems to me that by looking at an image of the planet and sort of scanning across it, you could certainly pick out the bright arms and the central nucleus, and you could tell by sort of scanning not just across but up and maybe up and down in those images, you could tell which way the galaxy was rotating. I mean, these techniques have been available for decades.
Yeah, so it's a good question. So it turns out that as a computer vision problem, like if you want to teach a computer to identify a spiral galaxy, it turns out it's quite easy, as you suggest, to do quite well. So in particular, if you're happy with sort of 80% accuracy, it's the work of an afternoon or so to code something up from scratch that works. But the trouble is, for the science we want to do, 80% accuracy is not much good. Because the effect, so the trouble is it's finding the pesky 20%, and indeed getting a method that I'm happy with, an automated method that's right 80% of the time, if it can tell me which 80% it's right about. And that's a tricky problem as well. So now I think we're getting to the point where spiral versus elliptical is a solved problem. We can do that one automatically now. But the more subtle ones about bulges and how many arms there are on bars, we still need a proportion of the data to be seen by volunteers. But it's something that our system's testing for. I don't want to waste people's time, and I don't want to ask people to do make work just because it's fun. So we do try, but it is true. Whenever I talk to computer scientists, they're all convinced they can solve this problem in an hour. and then they come back after an hour and discover that they've got 80% of the way there, but the rest of it's pretty tricky. But yeah, you're right. It's not an inherently intractable problem. It's just that the accuracy we need is high.
But I think you would be able to get that 80% with very high confidence levels, and that would leave you the 20% to focus on with human observers to do maybe deeper characterizations that the computers can't do.
Yeah.
I mean,
Yeah, and that's more or less what we're doing now. So that's true. But 15 years ago, that wasn't easy.
Okay, that's fair.
Yeah.
Other questions? Step right up. Step right up.
I
Well,
just talked very fast at all of you, so apologies for that. But there's a lot to talk about.
if I could ask, I guess, what is the most surprising or most interesting discovery made on Zoonovas? And what do you think, what's in the future for Zoonovas? What will it look like 10 or 20 years from now? And how do you see that it will change and evolve?
So let's do that one first. So I don't know about 10 years. I think I can think about 5 years in advance, or at least that's what we try to do. So I think that, let's take the Rubin Observatory with its 10 million alerts a night. I think in 5 years' time, most of those will be handled by automatic means. They'll have to be, but there'll be we'll have a system which we're building now that pulls out the most interesting. And my guess is participation in Zoonovas will be something like walking on the street and getting an alert that says that something's happened in a patch of sky that you and your friends are responsible for. And we need your help right now to figure out if we should point a telescope at it. And so that will mean logging on and seeing whether it looks like an artifact, whether it looks like a real thing, judging whether its pattern of brightness changes, looks like a supernova. So these are all tasks that we can teach pretty easily, but where distinguishing where we need human intervention. There's the trouble is that finding unusual things is reasonably easy automatically. But deciding which of the unusual things is interesting is really hard to automate. And so I think we'll need the judgment of hundreds of thousands of amateur astronomers and citizen scientists to do that. Your other question was about favorite discoveries and so on. So the most surprising thing to me is that Planet Hunters works. I sent an email that's notorious in the team the night before we launched that project. I was up at 2 in the morning, worried that we were about to waste everyone's time. Because it's one thing to look at an image and make a judgment, but Planet Hunters involves looking at graphs, look at brightness versus time. Mathematics deals with graphs, right? So it wasn't clear to me that we'd find anything at all. And it's still surprising to me that we find, I understand why it's happening, but it's still surprising to me that we still find planets that are missed by others. And then the most important is probably, I think, there's a class of galaxy called the green pea galaxies that I didn't get time to talk about, which they're called that because the volunteers found them in the background of some of these images. They're small, round, and green, and they're the most efficient factories of stars in the local universe. They're dwarf galaxies that have suddenly decided, for reasons that aren't clear, to turn all their gas into stars. And it's possible that they're the local equivalents of the galaxies that lit up the universe back when star formation was just getting started. And so by studying them, we can learn about the early part of the universe. And there are a couple of hundred papers of people arguing about them and looking at them and following them up. But they started with people doing the very simple thing of saying, this seems to be an unusual sort of galaxy.
Oh.
I also like the fact that the group of volunteers who found them and did the initial work on them called themselves the Peas Corps, which I didn't realize was a joke for a very long time. And then I said it out loud and realized, but yeah.
Well, thank you very much for that. Let me ask. Floor is open for questions. Anybody, please.
So
So
a large area survey telescope like that is going to discover a lot of things really fast. So if you have something like the soon to be launched, we hope, James Webb Space Telescope, if it survives its incredibly complicated journey to the L2 point, how there should be a lot of follow-on collaboration, I assume, between things you discover with something like that and say, like the green pea galaxies you were just mentioning. If there are that many of them and if they're that old, you should be able to see high redshift analogs of those with something like Hubble or James Webb. What do you think about that?
Yeah, I think that's right. I'm glad Hubble's around because James Webb, of course, is optimized for the infrared because it's looking mostly at the early universe. So, but certainly optical, I think, and Rubin will produce an enormous amount of need for follow-up, both with Hubble and James Webb. But in this country, we're very excited about the European Extremely Large Telescope as well, which is the 40 meter that's being built in Chile, and it's only 5 years or so from first light. So I think a lot of these objects will be targets for the ELT as well. I spend a lot of my time thinking about follow-up, and I'm mostly worried about the transients, the changes from night to night, because then we've got to make quick decisions. If we're going to follow up with James Webb, we can spend a few months and think about it. But if I have a list of things that the survey found tonight, I only have a few hours to tell our friends in Australia, telescopes in Chile. I've got a few hours to tell our friends in Australia what they should be pointing their telescopes at. And just the logistics of dealing with the data and getting it off the telescope and into computers and then around the world fast enough to make those decisions is actually really tricky. And so I think it'll take us a while to get good at that, but it's going to be fun for sure.
So will the Rubin also survey the sky in near infrared, like 1 or 2 micron? Or does it have that capability? Is it all visible?
No, it's optical, and it goes slightly into the infrared, but not much. So it's a bit, at least in this phase. So it's a 10-year survey, and then maybe we'll put another camera on it and do something else in 10 years. But yeah, it's a 10-year survey. And the other complication is that there's an enormous fight going on, very friendly fight, but the nominal design is scan the whole sky every 3 nights. But it turns out everyone who has a different bit of science has a different idea as to how to do that. So if you want to discover asteroids, you want to go near Earth asteroids, you want to go back to the same patch twice an hour apart, maybe 3 times an hour apart. And then if you do cosmology, you want the most stable images. So you want to use only the best nights in the best wave bands, and you don't care about anything that moves, you just go and stare. And so we're in the middle of an enormous argument to work out what pattern of movement actually makes sense. And yeah, so that's kind of fun too. All these things that we've never had to think about before, because we've never built a survey telescope on this scale.
Thankfully, I'm retired, so it's your problem, not mine.
Sure.
If you're worried about transients, that sounds like a job for this Wiki transient facility.
Yeah. So you can think of Zwicky as a sort of 10% LSSD. So if you scale that facility up by a factor of 10, that's roughly what the data stream will look like from Rubin. But we've done Zoonovas projects with the Zwicky transient facility people, which I should have mentioned in this talk. It's great fun. There's a great question on the chat. Beverly asks, how do you determine orbital periods with a light curve that only shows one transit? So that's because I put that plot up, which showed that. So there are error bars. You can get a first guess from the size of the transit. So that gives you, obviously you need to know the size of the planet, but the shape of the transit gives you an idea of the orbital period. We're often able to go and follow up and catch other transits. There's a really exciting source that I can't tell you about because we haven't confirmed it yet, that we predict will transit again next week. And so we have a bunch of people on telescopes around the world who will follow up. So we start off with a guess, and then we can go and check the guess by looking. So we have to do that. But it's a great question. And Joseph says, what other projects do you guys have coming up? Could there ever be an alien hunters project? We built that once. We built a project with the SETI Institute and Jill Tarter, working with data from the Allen Telescope Array. And we were looking at signals that came off the telescope and trying to identify unusual signals by eye. And it was a tricky task. And what we really want to do, one of the problems with doing that sort of SETI, where you're looking for unusual signals, is that most often when people find unusual signals, by the time you get the telescope back there, it's gone. And then you can't really conclude anything other than there was a signal. It was probably interference, but who knows? So we were trying to do it. So we got data off the telescope, and in 2 minutes, sent an alert back that told the telescope to interrupt what it was doing and go back and observe. And we never really got that working, and SETI was going through a period where they were struggling with funds, and we never finished it. But we built for that project, there were a set of badges that you could get that you would attach to your Facebook account. So, you know, I classified 10 things, or I'm participating in this alien hunting project. We built one for I have found aliens, and I've never checked code so closely as to make sure we weren't accidentally about to post to somebody's Facebook profile that they'd officially found aliens, as certified by the SETI Institute and the University of Oxford. So we were very careful. But yeah, that was a good experiment. I'd like to go back and try and do some of that with maybe some of the new breakthrough listen data or something. So that's you know, a serious answer to your question. But yeah, SETI is about finding the unusual, and I think we definitely talk to those people. Lynn, yeah, Stellar Sleuths is our new Stellar Sleuths project uses SWICKY data as well. So that's a good one if you care about stars in detail. It's one of the harder projects, but there's a lot to it, and the results look really, really good.
Well, we're going on almost an hour and a half, and
I should go and walk the dog. I think things have calmed down outside. So.
Professor Lintott, been very, very generous with your time. One more thing I'd like to ask before we conclude the meeting. Would you tell us about your most recent book, The Crowd and the Cosmos?
Ah, yeah, of course.
Right over
here. Yeah. So that's essentially the decent version of the story I rushed through tonight. So it's exactly the story of the Zoonovas, the people involved in it, some of the history, and some of the objects that we've discovered. And so it is translated into American for you. They actually paid a translator. And so you can either read that or you could read the British edition. But there's also, this has just come out this week in the States. So this is a book I wrote years ago with Patrick Moore, who was a TV presenter here, with and with Brian May, who is the guitarist from Queen, but also a PhD astronomer. So this is the complete history of the cosmos. It's rather smaller than you might expect. But the fun thing about this is we completely revised it with a colleague, Hannah Wakeford, who's an exoplanet person. And I think this is the most up-to-date public version of what exoplanets, these planet discoveries, are telling us about our own solar system and its history. So you can also buy Bang with 2 exclamation marks. But yeah, either is fine.
Very good.
Great. Thank you very much. And thank you for letting me plug the book. I hope to see you all again sometime soon. Take care.
And with that, again, Professor Lintott, thank you very much. Thank you for spending time with us this morning. Let me conclude the meeting with a word about our next presenter. The Greenway Talks Online will continue on Saturday, November 20th, when Dr. John O'Mara, Chief Scientist at Keck Observatory, will return for a presentation titled A Night in the Life of the Keck Observatory. in which he will guide us through the process of Keck Observatory's science, from research proposal to data collection to publication. He will show us how the observatory functions and how they support the astronomers at night while they're doing the observations. So with that, again, thank you to Professor Lintott. My thanks as well to everybody here for coming and supporting the Greenway Talks online.
Yeah.
And we'll see you in 2 weeks. And remember to set your clocks back or forward or whichever direction it goes. Okay, thank you very much. Bye-bye.